Good. Nico, my friend, in the previous unit, we learned that when charges move, they produce a magnetic field. I've showed you some demonstrations. Hopefully I've convinced you of that. Oh, and in addition, a magnetic field will exert a force on moving charges. Early in the 19th century, scientists such as Michael Faraday, one of my all-time favorites in England, and Joseph Henry in the US were aware of these, and they asked the obvious question. They said, look, if a current can produce magnetism, can a magnetic field produce current? And the answer is, yeah. We're going to be using some archaic terms because most of the notation and the terminology was given to us back, well, you can see when Faraday lived in the 1850s and 1840s when he did his research, and same with Joseph Henry. We're going to have to bring an archaic term. The archaic term is electromotive force, or EMF, symbol funky E. It's not a force, even though they used the word force back then. It's not measured in newtons. It's a voltage. It refers not to a force, but to the voltage of a cell. So voltage and EMF mean the same thing, and these symbols can be used, at least for our purposes, interchangeably. We're going to start to use the EMF symbol because we're often going to have, again, two V's in the same equation. We'll get around it by saying, let's use EMF for voltage and a little V for velocity, and we won't have to do the silly wings thing. And here was what Faraday and Henry asked. If a piece of wire moves through a magnetic field, the charges in the wire will experience magnetic forces. And if the piece of wire is made out of metal, those charges are free to move. Now, I realize it's electrons moving, but once again, we're going to do let's pretend it's protons, positive charges moving. And in fact, here's what we have. We have a length of wire L, and someone is pulling it down the page. Magnetic field, there's my high-tech graphics, it's into the page. What we're going to do is we're going to focus on one individual charge. Draw yourself a little positive charge right in the middle. Now understand, John, really this is trillions of positive charges all holding hands in this piece of metal. We'll just focus on one. Which way is that charge moving? What direction is the velocity? Down the page? Hey, this is good practice for right-hand rule on your upcoming test. Point your right thumbs down the page. Which way is the magnetic field? Into the page. Which way will those positive charges be forced? To the right. And which way will the negatives be forced? What you're going to end up doing is you're actually going to separate charges. You're going to get positives on this side. You're going to get negatives on that side. And holy smokes, Nico, what you've really just done is created the mechanical equivalent of a chemical battery. Because all a chemical battery was a positive terminal and a negative terminal separated by some distance. We've just done the same thing, but we've done it through motion, not through chemicals. We've done it through motion, not through chemicals. We have separated charges. Now that took work. That took work. As a matter of fact, it would require, you would actually feel a force resisting you as you were pulling this bar through the magnetic field because you were doing work on those charges. When I have my little generator flashlight and I hand it to Brian, turn it. You feel something resisting you. That is not because this is a poorly designed, lots of friction. What you're actually feeling is the force of those charges not wanting to be separated, and you're having to do work to separate those charges. That's the force that you're feeling. So, since the charges had been separated, which takes work, we have voltage. Why? Because we defined voltage as work or energy per coulomb. Well, we got charges. We've just done work. We must have voltage. We call this voltage induced voltage as opposed to chemical voltage because it was created not from chemistry like in a Duracell battery, but from motion. It's motion voltage. Let's see if we can derive an equation. Motion can induce an EMF. First of all, we defined voltage as potential energy per coulomb. Psst. Work on that later. Trust me. Potential energy, that's work done by the outside force. The definition of work was force times distance per coulomb. Which force? Magnetic force. What was magnetic force on a moving charge? Well, that was QVB from last unit times distance divided by Q. Oh! Maybe I was foreshadowing in the example that I did earlier, because what happens to the Q's here? Here they cancel. It turns out, hey, you want to know how much voltage you're going to induce? It depends on three things. How fast you're moving the metal bar, how big the magnetic field is, and how long the bar is. And instead of using D for distance, we're going to use L for length. And in fact, here is our new equation for this unit. The induced voltage, the EMF, is equal to BLV. Blum. And this is why we're using EMF. Otherwise, once again, we'd have a V and a V, and yeah, well, let's just avoid that. However, important constraint. All three of these have to be at right angles to each other. The direction that you're moving has to be 90 degrees to the way the bar is oriented, has to be 90 degrees to the magnetic field. If not, you're not going to get nothing. Let me show you what I mean. Turn the page. Here is almost the same situation as example 1. Almost. Except this time, the bar's length is in the same direction as the velocity. Let's still look at one little positive charge right in the middle. Let's draw him in. Which way is that positive charge moving, Jason? Down the page. Which way is the magnetic field? Into the page. Which way will that positive charge be forced? To the right. Except, can he move very far to the right in that thin piece of wire oriented that way? And yes, the negatives will be moved to the left, but can they move very far to the left if it's oriented that way? You really, Chelsea, you can't okay, technically you're separating the charges by, but you're not. You're not. You're not going to induce a good voltage across a distance. So what we're saying then is you have to make sure that the length, the velocity, and the magnetic field, what we're saying is you have to make sure that the length, the velocity, and the magnetic field are all at right angles to each other. And that's why it's a terrific application of your right-hand rule. Your right-hand rule is designed to solve this situation, by the way. That's why we came up with it. Let's look at some examples. Example 4 says, find the voltage. Oh, by the way, example 3, classic multiple choice question on your test. They'll give you 4 situations, pictures like this, and they'll say, which one will give you the biggest induced voltage? I guarantee in at least 2 of them, you'll have a bar moving in the same direction as your velocity. Oh, and if they're really nasty, the longest bar with the biggest magnetic field will be moving in the same direction as your velocity, because they'll really want to try and tempt you to pick that one. But it's got the biggest bar, it's got the biggest magnetic field. Hey, it's not perpendicular. You're not going to induce a voltage. Example 4. Find the voltage induced by motion across the ends of the moving wire and indicate the polarity. Are we at right angles to each other? Let's see. Length horizontal, magnetic field vertical, velocity. Ooh, what direction is the velocity? Into the page, our little X symbol. So yeah, we got right angles to each other. So we are going to induce a voltage. How big? Induced voltage is BLV. And again, that equation's on your formula sheet, obviously. Magnetic field, fairly big, 1.25, almost an MRI machine. I think the MRI video that I showed you was a 4 Tesla MRI machine, right? Length, not 80, 0.8. Velocity, 5.25. How many volts are you inducing? Sorry? 5.25? Really? The 1.25 and the 0.8 cancel? Okay. 5.25. You know what? That's almost a 6-volt D-cell battery. Now, there's better ways to do it than this, but we start out here. This is our simplest case. A much better way to do it is, instead of pulling something in a straight line, is to try and spin something, and we're going to have to really we're going to have to broaden our approach to try and work that in, but we'll start here. This is where Faraday started. Some applications, though. An airplane, a jetliner, which has a metal skin, that's basically a piece of metal moving through a magnetic field. Which magnetic field? The magnetic field of what? The Earth. And it turns out you do induce a voltage in an airplane. Now, which length am I going to use? The 60 or the 150? Which one is perpendicular to the velocity? The 60. So if I want to find out, oh, sorry, I forgot to do the polarity on the previous one. Which side of that bar is going to be positive? Let's see. Which way are we moving? Which way is the velocity? An example. Point your thumbs into the page. Which way is the magnetic field? Oh, this is great review for your test. Yes, we're flogging the right-hand rule to death today. Into the page, magnetic field down the page. Which side of this bar will be positive, the left side or the right side? Positive, negative. Right? But hopefully by now you've also clued in, if you can't bend your hand that way, raise your paper 90 degrees and then you probably can bend your hand that way, right? Thumb in the direction of the velocity in this case, because we're looking at one individual charge. Which way is the velocity? So point your thumb into the page. Magnetic field down the page. Boom, boom. By the way, good habit, Dorothy. If you're using mine, lift your paper up in front of you just so it's the same orientation. Because if your paper is flat and you're looking at mine, which is vertical, you might confuse yourself. I don't know. Example 5. What's the voltage that's going to be generated? Well, the EMF is BLV. The magnetic field at this altitude is 0.08. The length, you all agreed we're going to use the 60, not the 150. And the velocity of the airplane is 320 meters per second, just below the speed of sound. A little fast. Jetliners don't go quite that fast, but that's okay. How many volts? Oh, how many? 154 volts? It's my understanding that back in the 50s and back in the 60s, when they used to have smoking on flights, they used this voltage to power the cigarette lighters. The pop-out ones that you pushed in and then would pop out and be glowing red hot. I mean, it's sitting there, why not use it? It's not free energy. The energy's coming from their fuel in the long run. It lowers their gas mileage, but hey, it was a way to generate stuff. Now most planes have generators, because the nice thing with the cigarette lighters is it's unlikely that all 200 of your passengers are all going to push their cigarette lighter in at once. So you only needed a small current. Is it likely that all 200 of your passengers turn their televisions in the backs of their seats on at once? Probably. So now they have like generators and stuff. But clever. Oh, polarity. Here's our little positive charge sitting right in the middle of the wing. Which way is it moving? To the right. We need to know which way the magnetic field is. The question didn't tell you. Let's assume we're looking down at the airplane. So let's make a little note here. Assume the magnetic field is into the page. Then which side of this airplane would end up being positive? Sorry? The left, the up, the top, yeah. This will be positive. This will be negative, right? Right?
Sure.
Do it again.
So the velocity field?
Yep. Magnetic field into the page.
Yeah.
That's not into the page. That's along the page. Point your hand into. Point your hand.
This is into the page. Yeah. Okay.
Velocity into the page.
But how, because you can go like that,
No, you can't.
Yeah, you can.
Point your thumb that way. Your thumb has to go that way, right? Magnetic field has to go that way.
But if you go like that,
Well, that's not into the page. That's up the page.
how do you really get to the page? Oh.
Oh God, Gabby.
I said, quote, they didn't tell us the magnetic field, so we'll have to make an assumption here. That's what you guys voted for? Really? Wow. You know what? By the way, Gabby has raised a good point. On your tests, I will make sure I give you much clearer diagrams. Okay? In my friend who typed this up, he's the master of stick figure art, and it's great because I would not have wanted to type all this up myself. But on tests, I either pull a good professional diagram from the internet somewhere or from an old provincial exam, or I'll take the time on my tablet to draw something very, very clear. Next page. Another application, railguns. Okay? We're going to get to it in a second. But for starters, we're inducing a voltage, Jaron. If we got a voltage, we should be able to get a current. And we can. The easiest way is to take that metal bar that we're pulling to the right and just lay it down on a piece of conducting wire. So let's look at our little positive charge sitting right here. Someone is pulling that bar to the right, so that positive charge is traveling to the right. Gabby, what direction is the magnetic field in this question? We typed it in this time. Which way is it? So, thumbs to the right, fingers out of the page. Which way will that positive be feeling a force? Fingers out of the page, not into the page, out of the page.
Come on, Tyler. Come on, Tyler.
Ty, which way will that positive feel a force, up or down? Okay, but now, instead of just separating the charges, okay, folks? Instead of just separating the charges, now that charge has somewhere to go. In fact, now, because I've even put a little resistor, I've got a complete current. In fact, you can make an argument that this on the left is exactly as if, instead of moving a bar, I just had a battery right there. Because here your chairlift gives potential energy to the charges, gives them kick, and gets them moving. Here, the motion gives potential energy to the charges, gives them to a higher voltage, and gets them moving. But mechanically, they're equivalent. Oh, not only is there a current, but if we have a current flowing, then there must also be a magnetic force, because magnetic force was Bill. And this is where it gets not complicated, but cool. You see, Taylor, as soon as we start to pull this, which way does this positive charge feel a force? What direction? Down. Now, not only is it moving sideways, but what direction is it also moving? Down the page. So all of you now point your thumbs down the page. All of you now point your thumbs down the page. Magnetic field is still which way? Out of the page. Point my thumb down the page. Magnetic field, I got to bend like this, out of the page. Which way do these charges feel a force? To the left. In the opposite direction that you're pulling. That, Brian, is actually what you're feeling. When you turn this crank, you're feeling the resistive force in the opposite direction that you're trying to create the motion. It's circular, it's more complicated, but it starts here. You would physically feel something pulling against you, and the harder you pulled, the bigger force you'd feel in the opposite direction. Okay? Jason, you with me? Yeah? You sure?
Yeah, I guess.
Right? Because we got two motions now. Think of it as components or whatever. We got a horizontal being supplied by an outside source. But as soon as it starts to move, because now we're letting it move in a circle because we've completed a current, well, now it's also moving down. I've got a second component of motion, magnetic field out of the page. You know what? There's going to be a force opposite. And John, that's really the universe stepping in and saying, no perpetual motion machines, no free energy for you. If that wasn't the case, I could get free energy. But what this is saying is, the more you pull, the more the universe pulls back. To the left. Is that okay? By the way, good right-hand rule review for the test that you'll be writing on Friday, yes? Next page. So let's actually crunch some numbers. Here's a strip below. It's 12 centimeters long. It's moving at 4.7 meters per second. The external magnetic field is 0.08 teslas, and the resistance of the rail circuit is 0.025 ohms. Find A, the induced voltage. Well, induced voltage is BLV. Ben, what's the magnetic field? 0.08. What's the length of wire that's in the magnetic field, Ben? Don't say 12. 0.12. What's our velocity? What's our speed? It's a scalar, I should say speed. 4.7. How many volts will be created? 0.045. Which way, by the way? Well, let's look at our little positive charge right here. It's moving to the right. The magnetic field is out of the page. Which way will the current be flowing? Now, we're going to give this a name. We're going to call it CCW. What do you think CCW stands for? Counterclockwise. We're going to say the current can flow clockwise. Or that's clockwise. I'm sorry, it's not counterclockwise. It's clockwise. There's my first mistake of the day. We're going to call it CW for clockwise, CCW for counterclockwise. You can write out the words clockwise and counterclockwise, but there's your abbreviations. Okay? Convince yourself, Dorothy? Good. Dorothy, what does B want me to find? Well, you know what? Current is V over R. Right? Ohm's law. Do I not know the voltage? Didn't I just figure that out in part A because I said EMF and V are interchangeable? The voltage is 0.045, and I think they told me the resistance of this wire system in the question, did they not? What did they say the total resistance was? Oh, how many amps would we have flowing through here? 1.8? That'll give you a nasty shock. Jaron, what does C want me to find? On the strip, on the wire, you know what? The magnetic force on a wire. There's two magnetic force equations, QVB and Bill. Bill is for the wire. Magnetic field, still 0.08. Current, we just figured out, 1.8. L, the length of the wire, 0.12. How many newtons of force? .0173. Is that right? Yeah. Okay. Direction. Now, that force comes from not this sideways motion, because that's somebody else supplying it. That force comes from the current. Current's moving down in the wire. So point your thumbs down. Magnetic field out of the page. What direction? And you know what? It's going to be in the opposite direction of motion, because the universe is saying, nah, nothing for free. So the force would be to the left. Now, let's do some reasoning. Jason, what if I pulled faster? What would happen to the induced voltage? What would happen to the current? What would happen to the pull against me? Faster I pull, harder it pulls back. Okay. Does that make sense? Yeah. The faster you crank, the faster you crank it, oh boy, not going to go that good. Then Faraday asked another question. Faraday said, well, what if instead of moving just a single wire, what if I move a rectangular loop of wire? Well, I'm going to argue, Josh, that this is really 1, 2, 3, 4 separate chunks of wire. Let's treat it that way. So let's put a little positive charge in the middle of each one of them. Let's put a little tiny positive charge right there, right there, right there, right there. Let's do the back charge first. This guy. Which way will he experience a force? Well, he's being pulled to the right, so point your thumbs to the right. Magnetic field out of the page. Which way will that charge experience a force? Down. So he's going to get pushed that way. You know what? Let's look at the charge on the very front. Also moving to the right. Which way will he experience a force? Also down. So what you're going to have are two opposing currents. If you have two currents in opposite directions and they're the same size, what's your net current actually? Nothing. Zero. So he would, maybe we can generate something from the top one and the bottom one, though. Maybe. So let's look at that top charge. Which way will it be forced? Also down, except, wait a minute, that wire is so thin there, can we really separate charges in that thin wire? This is back to that section of wire is parallel to the direction of motion, not perpendicular. You're not going to induce an EMF there, and same with the bottom. In fact, is that okay for an explanation? Wait a minute, Mr. Dueck. I thought you said that coils and circles worked well. This bugged Faraday. We'll talk about what his solution was and what his momentous discovery was in a couple of days. But he was, I don't like this. Why is a single wire so much better and a coil of wire sucks? What's going on here? There's got to be some way I can utilize a coil. Yeah?
How does it cancel? Like, they're both going down, right?
Yep. So you can think of this as a little battery. Let's make up number 6 volts.
Yeah.
6 volts. We looked at batteries that were facing each other. When you had a 6 volt this way and a 6 volt that way, that was a net voltage of 0, net current of 0. Right? We did look at 2 ski hills in our circuitry unit. All right. Here is the technology for a railgun. Look, if I supply motion, that can create electricity and current. Doesn't that mean that current can create motion? Can't I reverse this whole procedure? So this is what, if you ever heard the term of a railgun, this is the theory behind it. This is what they're trying to build. They're trying to build something that will shoot a projectile using electricity. So in this case, Terry, it's the same diagram as before, but what have I put on the very, very left? A source voltage, instead of us supplying all the voltage. So it says the wire strip is initially at rest. Underline that. That's an important word. And there is a power supply in the circuit. It says for the circuit below, find the induced voltage. Well, induced voltage is BLV. Right now, how fast are we traveling? So what's my induced voltage, Nico?
0.
Nice recovery. You with me?
Yeah.
Because you weren't here. B says, what's the direction of the current? See the battery? Is the current going up or down from the battery? Down. So let's fill that in. It's going to be boom, 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 boom. In terms of a direction, clockwise or counterclockwise? Sorry? How come it does? I didn't hear. I heard. How come it does?
How come it doesn't separate the current?
How come it doesn't separate the current? I'm not sure what you mean.
Because like the next keep going.
Oh, yeah, but you know what? These aren't connected over here, so there's no way. It has no reason to go that way. Current wants to. Remember our Kirchhoff's rules. Current wants to go current in equals current out. There, current would go in but couldn't come out. You know what? That's a closed ski run, right? Counterclockwise. Now, what's the direction of the magnetic force on the strip? Well, look at that strip of wire. Which way are the charges moving in it? Up the page. Point your thumbs up the page, please. Magnetic field, which way? Out of the page? So extend your fingers out of the page. Which way will that strip feel a force? To the... Ah! So what's going to happen? D. What's going to happen to that strip? If it feels a force to the right, it's going to accelerate. How many of you have been on California Screaming at Disneyland? Okay. I need to go back and double check because we'll talk about why it might not quite be this technology, although it still could be if they make a modification, but we'll talk about that. Here's the start of a railgun. But as soon as this starts to move now, example 11, not only are the charges moving up this wire, what other direction are the charges also moving? To the right, because we've given them a velocity. So all of you now point your fingers to the right, your thumb to the right, magnetic field out of the page. Which way will the charges feel a force on them now? Down against the battery, against the current. Let's walk through this. As soon as it speeds up, what happens to the induced voltage? Increases, decreases, or stays the same? Here's our expression for induced voltage. As soon as the velocity increases, what's going to happen to your induced voltage? Increases, decreases, or stays the same? What happens to your net current then if now you have an induced voltage going in this direction? What happens to your net overall voltage? Bigger, smaller, or stays the same? Smaller. So what happens to your overall current? Bigger, smaller, or stays the same? Decreases. Why? Because current equals V over R. But it's really current equals net voltage over R. And now you've created a battery in the opposite direction of your initial chairlift. So your net voltage has gotten smaller, your net current gets smaller. What happens to the magnetic force then? Keeping in mind that magnetic force is Bill. What happens to the magnetic force? Decreases because your current got smaller. So what happens to the speed? Well, acceleration gets smaller. It's still speeding up, but it's not speeding up anywhere near as fast. It takes off like a rocket, but then continues to speed up slower and slower and slower. And this is why when I'm on California Screaming again, I'm going with the basketball team next year at Christmas time, I need to try and feel, does my acceleration increase when they launch me, or does it decrease when they launch me? Because if it decreases, then they are using exactly this system. Oh, however, there could be a workaround. What they could do, John, if they want to have a constant acceleration, they could juice this voltage up at exactly the same rate as this one is increasing, so you could still end up with a net constant voltage. So maybe there is a workaround. I got to find out, because that's the only ride, at least here on the West Coast. I think maybe Six Flags might have some, but that's the only one, as far as I know, that launches you as a roller coaster instead of using potential energy to start the roller coaster, right? In fact, what would happen if this got faster? What would happen to the induced voltage? Bigger. You know what? Eventually, you'll reach a magic number when the induced voltage equals the source voltage. When the induced voltage equals the source voltage, what's your net voltage? 0. What's your net current then? 0. What's your net force? You've maxed out your speed, now you keep going at a constant speed. That's the fastest this railgun can launch you at. And we'll actually calculate an expression for maximum speed a bit later on. But let's try some numbers. Oh, explain your answer using relevant physics principles. We just did, yes? Some applications, some cool applications. This could be a method to launch space vehicles from the International Space Station without rocket fuel, because you really don't want to be firing a rocket backwards at the space station as you leave. So what you would do is you would put a conducting wire. You would have the spaceship itself be the conducting wire. So let's fill this in here. Here is our big battery supplying current. So the current is going down the page in my spaceship. Point your thumbs down the page. Which way is the magnetic field in this particular picture? Into the page. Which way will the spaceship feel a force? Forwards. And there, away it leaves the space station. You could do this with current technology. Those two big magnetic fields could come from some big solenoids, and you could power the whole thing with solar cells. Doable. Probable, in fact. Most likely that'll be a fairly easy, low-tech, few moving parts way to launch space vehicles. Once it's, all you got to even do is get it just a small velocity, because in outer space, once it has that small velocity, will it ever slow down? So it'll drift, and once it's far enough away, then it can fire its rockets. Bigger velocity is more convenient, but you can control it quite accurately. Another application, it turns out, is going to be in electric motors. It turns out as soon as you turn an electric motor on, it is also generating a voltage in the opposite direction of the voltage coming from the plug. We'll talk about that in a whole separate lesson. Example 12. As the strip continues to speed up, albeit at a lesser rate, the induced voltage will continue to grow. What happens when the induced voltage is equal to the supply voltage? Well, what would your net voltage be if your induced going this way is equal to your supply voltage?
0.
What will your net current be if current is V over R? 0. What will your force be? 0. Therefore, since F equals ma and m's not 0, what will be 0? Well, if you have no acceleration, what's the correct answer, A, B, or C? Yep. It says explain your answer. There. It's exactly how I'd answer it. No English. I'd say, you know what? I know my net voltage is 0. That means my net current is 0. I even did a little proof of why my net current would be 0, but I'd probably accept that as being fairly obvious. I did a little proof why the force is now 0. Hey, that means acceleration is 0, constant speed. Now, in real life, Jason, there would be a little bit of friction slowing this guy down, but as soon as he slowed down, now this voltage is a little bit bigger than this voltage, which means you have a little bit of a net force. Going to speed it up again. It's going to kind of, and then just hit its constant speed and keep going. Find an expression for the maximum speed of this railgun. Okay. Well, the maximum speed is when right? When your source voltage equals your induced voltage, because then your net voltage is 0. When you want the maximum speed, looks like it's whatever your source voltage is divided by the strength of the magnetic field and also divided by the length of the wire. So back in the first Gulf War, the one that occurred before you folks were born, at one point in it, the U.S. military stopped some cargo ships that were heading to Iraq, and those cargo ships claimed that they were carrying long pipes for oil drill rigging and things, but the U.S. believed that these long rails were for a rail gun. How accurate was their intelligence? I don't know. We believed it at that time. But in the second Gulf War and invasion of Iraq, we've learned that the U.S.'s intelligence isn't quite as intelligent as they thought, right? There's weapons of mass destruction. Didn't find any, so they were wrong. But anyways, that was in the news, that there'd be these long tubular structures, and they thought this is part of trying to build a railgun, a cannon that shoots things using electricity. How fast can you get? Let's try doing some number crunching and find out. Example 14. For each instance below, find the induced voltage, the net voltage, the current and direction. By the way, the net current and direction, and the magnetic force and direction. You know what? Since there's two situations, before and after, let's draw a line right down the middle of the page here. Okay. And let's do each letter for each one at the same time. In other words, let's do A for part situation and A for that situation. What's the induced voltage for the first situation? This is really easy. Induced voltage is BLV. What's the induced voltage for this first situation? 0. Why? V is 0. Hasn't started moving yet. The induced voltage in this situation is also BLV. We are moving. And I quickly double-checked. Everything is at a nice 90-degree perpendicular angle to each other. We are going to get an induced voltage. It's going to be 0.35 times... Oh, it says 4.1 meters in the picture. I had to go look for that. 8. 11.5? B says, find the net voltage. Well, again, in the first situation, that's easy because nothing else is going on. 320 volts, it's your source voltage. Here, it would be, you got a 320 volt source, but in the opposite direction, you've got 11.5 volts. You've got a little chairlift pointing against it. 308.5? 309? Yeah?
Where do you get it?
Right? Because that voltage is always going to be in the opposite. You get nothing for free, Dorothy. That voltage is being created against the voltage that's causing the motion. Is that okay? So I'll go with 3 sig figs, 309 volts, 308.5. C, the current and direction. Well, current is V over R. 320 over Looks like the only resistor is 8.5 ohms. How many amps are flowing through the left-hand situation? 38 even? 37.6? Volts? No, amps. In the second situation, current is still V over R, but it's your net voltage, which is going to be 308.5? I wrote 309, but 308.5 divided by 8.5. What's my net current here?
6.3.
By the way, direction. In the first situation, I'm pretty sure the current is leaving the battery going up. Oh, I did it again. Good gosh. I've got volts on the brain here. Thanks, Ty. What's the direction of the current in the first situation? Clockwise or counterclockwise? Let's put a little CW there. Now, in the second situation, I think it's still clockwise because I think the battery is still winning. Yes? In fact, it'll never be counterclockwise. It may hit 0 when you max out your speed, but it'll never be counterclockwise. Brian, what's D asking me to find? Oh, force? Bill. Force. Bill. Magnetic field, 0.35. In fact, it's 0.35 for both of them. But the current is different for both of them. In one, the current is going to be 37.6. In the other one, the current is going to be 36.3. Same length for both of them, 4.1. 4.1. What do you get for the force on the left-hand side? How about 54 newtons? Direction. Well, let's see. It looks like in this wire, the positives are moving which way?
Down.
Down. Magnetic field into the page. To the right. To the right. Second force, slightly smaller current, 52.1 newtons, still to the right, just not as strong. As this speeds up, what happens to my answer for part A on the, what happens to this number as I speed up? Gets bigger. What happens to this number as I speed up? Gets smaller. What happens to this number as I speed up? Smaller. What happens? You know what? Let's find out the maximum speed. When does, we got room here, yes? When does that occur? When my voltage equals my source voltage. When my induced EMF equals my source voltage. It occurs when that equals that. Right? It occurs, if I get the little v by itself, that divided by, I'm just curious how fast this railgun can get this thing. What's our source voltage? Was it 320? Yeah? No? Yes? No? Yeah? 320 divided by magnetic field is 0.35, 4.1. What's the maximum speed this particular railgun can fire a projectile?
200.
Wow, really? It's got some good speed. Now, Gabby, that would require a long enough rail for it to reach that maximum speed, and that's why I mentioned the story of in the first Gulf War. That was the parts that the U.S. claims to have intercepted, parts to build a nice long rail to get up to speed. Okay. Induced EMF, kind of some cool stuff, I hope. What's your homework? I'll give you the same questions I assigned my block Bs. Oh, and there's a lovely little comic there, by the way. The very, very, very bottom. Yes, of course, I'm sure this is the magnetic North Pole. But who the hell left that bloody great solenoid here? Yeah, okay. I assigned 1, 2, 3, 4, 6, 7, 8. 1, 2, 3, 4, 6, 7, 8. But I have a feeling many of you are working on stuff from the previous unit, and that's also fine too. Just don't fall too far behind. 1, 2, 3, 4. By the way, 5 is cool. I'm not going to assign it, but for what it's worth, if you wanted to figure out how much power, how many watts you needed, there you can easily then, because you know current, you know voltage, power is VI, or power is I squared over R, or power is V squared, you got all sorts of options. You can calculate how many watts of power. 6, 7, 8.